Okay, let's go ahead and get started. Hello, everyone. I'm Charlie Smith, Principal Consultant with ESIG, and I also serve in a leadership role with the Global Power System Transformation Consortium, or G-PST, whose mission is to bring together key actors across the globe to catalyze a rapid, clean energy transition at unprecedented speed and scale. This is being done by providing a coordinated and holistic approach to the necessary knowledge, education, and support to power system operators across the 5 action pillars. At the core of the G-PST is a large cross-section of system operators from around the world who are dealing with a rapid transition from a system based on synchronous machines to one built around inverter-based resources. The 5 pillars of the consortium include research and peer learning, technical support, workforce development, standardization, and open data and tools. ESIG is the co-lead on Pillar 1, along with Mark O'Malley of Imperial College. And more information on the G-PST can be found at globalpst.org. As a co-lead on Pillar 1, ESIG would like to welcome you to the February monthly webinar of our joint G-PST Pillar 1 ESIG webinar series. This series is in addition to the regular ESIG monthly webinar series and focuses on the G-PST research agenda and associated topics being addressed in Pillar 1. Topics are presented by both system operators as well as members of industry and the research community. An additional series of webinars on the other 4 pillars of the G-PST is also being provided on a monthly basis through NREL. For those of you who would like to learn more about the G-PST and how to engage, please go to globalpst.org and click on the Get Involved tab. Further information on ESIG can be found at esig.energy. Next, I'd like to go over a few logistical matters before we get started. First of all, lines will be muted for the duration of the webinar to avoid unnecessary distractions. For the Q&A, we'll use the Slido platform at slido.com. To ask a question, please navigate to slido.com and enter ESIG26 as the event code. The instructions are also at the bottom of the screen. You'll see a thumbs up button next to the questions on Slido to allow you to cast a vote to help prioritize the questions submitted. We plan to save about 10 or 15 minutes for Q&A at the end and then wrap it up at the top of the hour. An email with a link will be provided once the video file has been posted. We also plan to provide short responses to unanswered questions after the webinar, so please don't be afraid to ask your questions through Slido. Today's topic is on reliable energy forecasting for power system operations. As you might imagine, with the changing nature of the resource mix due to the retirement of conventional generation and its replacement with variable renewable energy resources, many aspects of the system design and operation are going to be changing, and this is just one of them, but a vitally important one as it represents the critical function of keeping the load and generation in balance on a minute-by-minute basis to maintain reliable system operation. This is a topic that has been around for quite a while and continues to be one of high interest and critical importance to the industry. Energy forecasting tools deployed in operational processes are increasingly based on machine learning methods, with the resultant forecast subsequently used as input in decision-making tasks, such as market clearing or scheduling. This opens the opportunity for novel ideas to improve the reliability of energy forecasts and the resulting operational decisions. One of the novel ideas that will be presented here is a smart predict and optimize approach that embeds knowledge about the downstream decision task during model training, leading to more economical and robust decisions. Operations forecasting is one of many areas where AI machine learning techniques are being applied to power system applications and have been for quite a while. Today's webinar will introduce some new ideas in this field and will be presented by 2 members of the research staff working with our Pillar 1 co-lead, Mark O'Malley, at Imperial College in London. They are Akylas Stratigakos, who received his PhD from Mainz in Paris, and Wangkun, who received his PhD from Imperial. Over the past few years, I have come to greatly value and appreciate the work Mark and his research group are doing, and the leadership they are providing to the industry and to G-PST, and I look forward to hearing what they have to say. Okay, just a short reminder once again to use Slido at slido.com with the event code of ESIG26 to ask your questions. Let's go ahead and get started. Akylas, I will now turn it over to you.
Okay. Thank you very much, Charlie. Presenter mode. And okay. So thank you very much, Charlie, for the great introduction, and also thank you for the wonderful opportunity to be here today and to present our work on energy forecasting for power system operations. So we're going to present two, let's say, innovative ideas about the resiliency and about maximizing the value of our forecast. Before we start, a brief overview of our team at Imperial College. So we have established at Imperial international partnerships with universities across the globe through the Electric Power Innovation for a Carbon-Free Energy Society Center. So the center is called EPICS, and we have established collaborations with institutions from the US, Australia, and the UK. We acknowledge funding from partners and research bodies across all continents. And we also engage in stakeholder engagement, primarily through ESIG and through the Global Power System Transformation Consortium. One example of this stakeholder engagement is an AI workshop that was hosted by the University of Edinburgh last February, where we scoped the potential of artificial intelligence to address some of the key research questions that appear in the G-PST's research agenda. Our team at Imperial is quite large and keeps growing. We have a quite diverse body of researchers that conduct holistic research to support the transition towards low carbon power grids. So we have people working on IBRs and grid stability. We have a group of people working on techno-economics and strategic pathways to decarbonization. Another group of people focuses on services for renewable, for grids that are based 100% on renewables. And we also have a research on decision support, and this will be the focus of our presentation today. So in this research thrust, we utilize methodologies such as machine learning and optimization to take advantage of the wide variety of data that are available to us and to develop forecasting and decision-making tools to support the power system under a high penetration of renewables. Charlie gave a great introduction about the context of this work and the importance of energy forecasting. As we all know, the grid used to be fairly centralized, and operators had to deal with limited uncertainties, for instance, the relatively predictable demand. Nowadays, we're increasingly facing a more uncertain variable environment. And in the future, this will become even more so with the advent of distributed energy resources and behind-the-meter generation. So we hypothesize here that we can utilize the data that has become available through grid digitalization, and we can use smart methodologies such as artificial intelligence to maximize the potential of our current infrastructure. So energy forecasting in particular is critical for the safe, reliable, and economic operations of our system. It helps us improve our operational awareness and is the first input in risk management processes. And of course, we also use it in market clearing processes and service design, for instance, to decide how much reserve to procure. And I want to mention here that in this presentation, we will be focusing primarily on short-term forecasting for an operational planning horizon. So our methodologies and the focus here is for uncertainties that are realized from a few minutes to a few days ahead. So energy forecasting for this time horizon is a quite mature technology. However, we posit that it's time to go beyond the traditional accuracy-oriented notion of forecasting. And we need to ask ourselves questions such as, do our forecasts lead to better actions, so safer or more economical actions? And second, these forecasting models have been integrated in our operational pipelines. So are we sure that we can trust them under adversity? So in this presentation, we're gonna present methodologies that bridge machine learning with traditional optimization to achieve two goals. First of all, to make these pipelines, these forecasting pipelines resilient to adversarial inputs. And second, to maximize the value of our forecast given a specific business case. A little bit of a historical overview of forecasting through the years. In terms of application, the primary focus has always been the demand, which was fairly predictable up until the 80s. We began to become more interested in wind power forecasting in the late 80s, early 90s, and after that, solar power forecasting. And nowadays, we're also increasingly interested in applications such as forecasting for EVs, forecasting for smart meters, and anything related to DERs. In terms of methodologies, when we didn't have to deal with much uncertainty, we used techniques such as lookup tables, which are fairly simple. We increasingly became more interested in using the weather as input in our models, and we have, since the late 80s, the advent of machine learning. And I know for a fact that some operators have been using machine learning forecasting models operationally, at least since the 90s. Starting in 2000s, we became increasingly interested in probabilistic forecasting, so how to quantify uncertainty, how to use this forecast. And another thing of interest nowadays, especially for distribution grids, would be how to deal, for example, with privacy concerns, or how we make forecasts when we have little to no data available. So to set up a common, let's say, terminology and background, we have an example here of a forecasting pipeline. So our goal in this example would be to predict the aggregate net demand in order to schedule production for the next day. So how we proceed by doing this? We have input coming in from different sources. In this case, we have a weather forecast from a service provider. We have historical observations, information about the day of the week, and potentially some special event that might occur in the next day. We found ourselves an origin, we found ourselves at an origin time, and we want to predict the demand for the next day, which means a horizon from 12 to 36 hours ahead. So in this case, we can derive different types of forecasts, and each type of forecast is useful for a different process. The most commonly used is what we call deterministic or point forecast, indicated here with a black circle, which in effect represents the most plausible value. We also are interested in quantifying the uncertainty. Here I have visualized an example of a prediction interval that indicates 90% probability that the true realization will fall within this range. And we can also have scenarios such as the ones indicated here in gray, which are considered to be samples from a distribution that account for spatial and temporal correlations. And we use point forecasts, which are the primary, let's say, types of forecasts. For instance, to schedule the production for the next day. We may use prediction intervals to set up reserve requirements if we want a specific reliability level. And scenarios have also been used as the first step to a downstream contingency analysis. So this pipeline, we can abstract it into a simpler model chain that goes from data to decisions. So in effect, we have our data coming in. This is an input into a forecasting model. The forecasting model outputs some predictions, and these predictions represent some sort of parameter in a decision-making problem. We solve this decision-making problem, and then we derive some set of decisions or actions, which are fed into a downstream control module. So in this presentation here, we will focus on two aspects of this model chain. The first one is what happens when we have a disruption in the flow of information and how can we seamlessly adapt to missing data operationally. And the second one is to bridge and integrate the downstream decision-making process with the training of the forecasting model in order to maximize the value of our predictions. I will be presenting the first part of this presentation. So here we are interested in forecasting with missing data. We consider the following settings. So as an operator, we gave to a forecaster or to an analyst a data set and a forecasting task. The forecaster trained and offline tested a model, and now we have this model deployed operationally and used in production. However, this model assumes a constant stream of information, and in some cases, we might face some sort of disruption, such as an equipment failure or a cyber attack that compromises this flow of information. For instance, a recent survey by the European Commission about the ENTSO transparency platform indicated that fewer of 40% of the platform users were 100% satisfied with the timeliness that they received their data. And we hypothesize here, of course, that if we have a disruption in the input of this model chain, this will compromise forecast accuracy and it will propagate into suboptimal and perhaps riskier decisions. So the question we ask here is, how can we make this model chain resilient to missing inputs? And how can we make sure that we are addressing this missing input problem in a fast manner that complies with strict time constraints, so we can deploy this operationally in real-time production. As a motivating and guiding example here, we have the case of short-term wind power forecasting, which is quite common. So we have a fleet of wind power plants, and our goal is to generate production forecasts in a very short-term horizon from 15 minutes to 4 hours ahead. And this is quite typical, let's say, used for instance, for reliability scheduling algorithms. And we assume that our input is current and past production measurements from adjacent plants and potential information about the weather in the following hours. And this is the input in a model which could be a simpler linear model, or it could be something more complex like a neural network. And we're going to explore here what may happen if we have an equipment failure and we don't get the latest measurements. So what we found through stakeholder engagement that usually happens from an industry perspective is that if we have missing data, such as missing production measurements, we implement what is called a persistence forecast. So basically, we take the last measurement and we are forward filling into the future by propagating this ahead. And this is a quite fast and effective way to impute missing data, but we believe that there is a performance gap here and we can do much better. Some other industry stakeholders mention that what they do is actually they wait to see what type of information they receive, and then basically they retrain a new model that only considers this the available information. And in some theoretical sense, this is the optimal thing to do because the lower expected error. However, it is computationally costly to implement on the fly during real-time operations, and also accounting for all the combinations of missing input data becomes quite impractical quite fast. So what we are proposing here is what we call adaptive forecasting models. So we train forecasting models as we usually do, but in this case, the model parameters learn to adapt to the availability of input information. And to illustrate this, we have a toy example, let's say, that is useful to guide you through this application. So if we consider a simple forecasting model that has 3 inputs that may be unavailable at some point. So we begin by finding the whole space of possible combinations of missing inputs. And here we estimate an optimistic and a pessimistic worst case set of parameters. And this provides 2, let's say, loss bounds. And these loss bounds can also, we can also retrieve a loss gap. So the optimistic parameter. The optimistic case is that all the features will be available. We implement this algorithm at the beginning, and then we deploy an adversarial agent that searches to find what is the most critical input that if it goes missing, it will degrade the performance of my model. In this case is input 1, and we use this to split, let's say, to partition the space of possible combinations of missing inputs, and then we repeat this training process recursively. And what this allows us to do is to, first of all, identify in a data-driven way what are the critical scenarios of missing inputs, and then have our model adapting to these realizations of uncertainty. And this has, during real-time operations, this incurs no additional computational cost, and even so, it does not depend on having historical training datasets with historical missing data patterns. So it can learn from, let's say, complete training datasets. And to illustrate what this approach would mean for the short-term wind power forecasting case. So here I have zoomed into the, let's say, vicinity of our target power plant. So we assume that our target power plant is power plant 2. And we assume that our features, so the inputs that we are using for prediction, are the current measurement of all the power plants in this vicinity, plus 2 historical lags, so period T, T-1, and T-2. And we also have one input that accounts for the weather into the future. And we assume we have a simple linear model to train. So by training this model here, assuming all information are available, we can sort of extract an idea of which input is the most critical for performance. So in this case, we can see that the highest weight in an absolute term has been assigned to the current measurement at period T of the target plant, which is power plant 2. Our algorithm identifies this as the most critical input and then decides to split the feasible space of missing data into 2 cases. So if this measurement is missing and we retrain our model, we see that now the distribution of these weights has changed, and the most critical feature is the current measurement in an adjacent power plant. In a sense, our algorithm here identifies these critical features and finds the worst case scenarios, and after finding a few critical ones, deals with the rest of the scenarios using robust optimization. And this process progresses recursively. As an example here, we ran extensive experiments on short-term forecasting with missing data, and we consider 4 horizons, so from 15 minutes to 4 hours ahead. In this grid of plots here, we visualize the root mean square error performance, so the forecast accuracy, versus its time horizon. So we see that for 15 minutes ahead, performance is quite good, and as you go into the future, naturally, performance starts to degrade. So in this case here, we examine what is the best case scenario. So we have no missing data indicated with a dashed line versus what happens when we have missing data and we use the industry standard imputation approach and 2 of our proposed methodologies. To guide you through this graph, so as you move from the left to the right, we have disruptions in carrying more frequently. So we may have an equipment failure in carrying at more frequently. As you move from the top row to the bottom row, conditionally on disruption occurring, we have this disruption having a longer time period. So basically on the top, when we have missing data, it is missing for shorter periods, and at the bottom, it is missing for longer periods. So the best case scenario of least missing data is top left, and the worst case scenario of most missing data is bottom right. In effect, in the first row, we only have missing data that occurs only for 15 minutes. And what we can see here is that the imputation, which is a standard approach, is quite good and basically performs on par with the theoretically optimal performance. However, we see that as we increase the period of missing data, that are missing for longer periods, performance starts degrading for the imputation approach quite considerably. So in this worst case scenario, we see that we get an RMSE of approximately 15%, while the proposed approach manages to hedge against the risk and maintains an RMSE that is lower than 10%. So in essence, our adaptive models are on par with imputation when data are missing for short periods and considerably better when data are missing for longer periods. And in this case, what we have managed to achieve is that we are hedging against worst case scenario. And we do so without additional operational cost. And these are results that pertain to a case of a linear forecasting model, but similar results are observed for the case of more complex models such as neural network. And with this, I conclude my part of the presentation. I will give the floor now to my colleague Wangkun to talk about application-driven energy forecasting.
Right. Thanks, Akylas, for the detailed introduction and this comprehensive analysis on the impact of missing data and how to deal with it on an energy forecaster. So my part focuses more on how to maximize the value of our existing energy forecaster by using the application-driven forecast framework. So some of this work is done during my PhD study that was funded by the EEE department at Imperial College London, and with my supervisor, Dr. Fei Ten, while some ongoing effort is supported by the APIX UK project. All right, so let's get started. First, I would like to recap on the pipeline of how to building an energy forecaster in a very general way. So starting with the data source, such as some, as mentioned by Akylas, such as weather forecast, some calendar informations, and some previous observed energy profiles, the practitioners can choose a dedicated forecast model that can best fit or describe the data. And however, to fairly evaluate the performance of the forecaster, some of the evaluation metric must be proposed and used as the loss function during the training. In most of the cases, some statistic criterion such as mean squared errors are used. And based on the types of the data, the module, and the loss functions, a suitable training algorithms is used to iteratively update the forecast parameters with the purpose of minimizing the loss function. While this pipeline works relatively well and will be followed in the future, however, there are indeed some new challenges and opportunities in the grid. First of all, the main challenge is the large penetration of renewable energies, which makes most of the energy forecast less reliable and unstable due to its uncertain nature. Well, of course, some new opportunities exist, and thanks to the digitalization of the grid, there are more and more data from diverse sources available to train the forecaster. Therefore, to improve the forecast accuracy, practitioners mainly focus on innovating about building more dedicated and more complex forecast model structures, such as some of the state-of-the-art transformer models and the state space models. Because of the main target of this type of forecast is to maximize the forecast accuracy, in this presentation, it is referred to as an accuracy-driven forecast. Next page, please. Okay, so we keep thinking, so what else can we do? Of course, as a power system engineers, we know that how this forecast will be used in the follow-up activities, and this what we call the downstream decision-making, such as operation and control. And we kind of agree that the accuracy of the forecaster, or you can see the error of the forecaster, will be eventually reflected or uncovered by the operation cost of the generator. Therefore, there gives another direction about forecasting is instead of purely maximize the forecast accuracy, so how about we improve the value of the forecaster, which is associated to the any activities we would like to define. And in this situation, what we would like to do is to design some tailor-made loss functions that can better align with the power system decision makings and of course the associated operation cost. So because of the new training target is to maximize the values of the follow-up activities or applications, this presentation will refer as this type of forecast as an application-driven forecaster. Okay, next slide. Okay, right. So here in this slide, I would like to give a direct comparisons between accuracy-driven and application-driven forecast pipelines. Well, the main difference is that in the accuracy-driven forecaster, the training objective does not match the final objective at the application stage. For example, what we really care is to maximize the economic benefit. However, in this kind of training pipeline, the training loss is associated with the forecast accuracy instead of the value of the follow-up decisions. And therefore, the training stage and application stage, they are actually mismatched and separated. While in contrast, in the application-driven forecast, the value of the decisions or the value of the reflection of the forecast on the activities is explicitly used as the training loss in the offline training stage. Therefore, by this kind of design, the trained energy forecaster will be more and more aligned with the operation cost. Therefore, I think the main takeaway, I just would like to summarize this slide, is that what you train will become what you get in reality. Therefore, for AI to make economic or reliable decisions, the conditions it faces in reality must be faithfully reflected and respected during its own training. Next slide. Okay, so I think it's about the time to introduce some case studies and demonstrate the performance of the proposed algorithms of our study. So we will mainly focus on a centralized power system operation task at a transmission level. And the system under test is a standard IEEE 14-bus system with some open data, which composed of grid configurations, weather data, and energy profiles from open source reference 1. And our forecast target is an integrated load and renewables at multiple locations, or you can see buses in this standard system. And two sequentially connected decision-making process, which is unit commitment and redispatch will be considered. So it is by now becomes very obvious that why this example is particularly picked up. This is because this is exactly a replica of a prediction and or forecast plus an operational optimization task. So start at the very beginning, you have the backbone of the conventional energy forecaster, which has a data energy forecaster, which we're particularly interested in is a neural network-based forecaster. And then the forecast energy profile will be fed into a unit commitment problem, followed by a clearing or balancing problem at a near real-time redispatch problem. And the operational cost is a integration of the cost from both stage 1 unit commitment and stage 2, which is a redispatch. Right, so here, before I go to the discussion about the performance of the algorithms, I would like to provide some details of about the forecaster. So because we are using a neural network-based forecaster, we're considering a more complex problem, which is a multivariant time series or energy forecast problem. So the input of this task is of 3 dimensions. So the first dimension is a time steps, which we consider during a day ahead, 24 hours predictions. The second dimension is the number of nodes. It's 14 because it's a 14-bar systems. And we have 10 features plus some previous energy profiles, which we also include as the feature. And the output size, which is similar to the input, it has 24 hours and as a time step. And the forecast is the number of load, which is 11 in this system, plus the number of renewables, which is 4. And the total number of parameters or trainable parameters in this neural network is around 16,000. And the total size of the data set is of a year, which means 1 hour resolution. So an overview of the performance of the application-driven forecaster compared with the accuracy-driven one. And operations, of course, on the true data is summarized in this table, and it is all based on the average performance on the test dataset. So as you can see, our proposed method, maybe not surprisingly, we actually have a worse performance on the forecast accuracy in terms of mean absolute percentage error. You can see there is a 1% higher compared to the accuracy-driven one. However, the cost of our proposed method is actually reduced by around 4%. If you're considering the capacity of the system, this kind of cost reduction can be very meaningful. Then, at last of my presentation, I would like to show some scatter plots on the load and renewable forecast error. So on the right side of this page, so the x-axis are the average forecast difference as defined as the forecast value minus the true target, and we call if this value is negative, we call it as an under forecast, and if it is positive, then it is a over forecast task. So Akylas, can you click? Yeah, thanks. Well, as you can see from the accuracy-driven forecast, which marked as the blue points in the figure, you can see that the under forecast on load or over forecast on renewables is more costly. This observation is because the generators and reserves need to be rescheduled more frequently and more costly at the near real time. Therefore, what application-driven forecast becomes powerful is that, as you can see in the orange point, it actually tends to over forecast the load and under forecast the renewable, which did the opposite things compared to the accuracy-driven forecaster. And of course, there are more reasons why we can achieve a better operation cost. The main issue is the complexity and nonlinearity we included by directly encode the optimization as part of our neural network-based forecaster. I think that's all of my presentations. I'll hand over to Akylas to summarize our work. Thanks.
Yes, thank you very much, Wangkun, for the great and very interesting presentation. So, to summarize our work that was shown here today, so on the first part, we dealt with the resiliency problem in our forecasting pipelines, and we developed methods to seamlessly handle missing data operationally. So the proposal is to make the parameters of our model adaptive to the availability of input information, and this does not require any additional computations operationally, so it's lightweight and can be deployed within operational pipelines, and it also provides hedging effectively against worst case scenario. In the second part, Wangkun presented about application-driven forecasting, which in effect integrates mathematical optimization with machine learning in order to maximize the value of our forecast, considering a downstream decision-making process. And an important feature here is that this can be integrated with any existing pipeline, and there is no need to actually change the downstream decision-making problem. So we don't need to stochastically clear the market. We can use deterministic forecasts, but ones that minimize, let's say, for instance, decision-making cost. And there is a lot of ongoing and exciting work at this moment. So one particular two things I would like to mention. First of all is our work on forecasting reliability constraints in order to improve market clearing processes and operations. So for instance, how can we forecast a few critical inequalities which we could add to market clearing in order to ensure higher deliverability of reserves. And another interesting work that is ongoing is extending the integrated forecasting and optimization framework to also include controlling the loop. And with this, we'd like to thank you all for listening, and we'll be happy to further discuss with you.
Thank you, Akylas and Wangkun. While we're waiting for a few more questions to come in, I know you have some interesting information on forecast combinations that you're kind of holding in reserve. Why don't we go ahead and cover that, and before we get into the questions?
Yeah, great. So in the context of application-driven forecasting, we have also a more niche, let's say, work that is application-driven forecast combination. And I know this is an interesting topic, forecast combination, for many stakeholders. So in many cases, operators, they do not generate their own forecast. They have external vendors for this. And even since the 60s, it is quite known that getting multiple forecasts that are quite diverse and combining them can lead to much better accuracy. And actually, this work, funnily enough, was motivated by an ESIG webinar that took place last October, I think. It was presented by Amber Motley from California ISO about the advances in the use of wind and solar forecasting. So according to that presentation, the California ISO implements what they call multi-vendor optimization. So they get forecasts from different service providers, and then an expert utilize their knowledge to I think, to select which one will be used operationally. So the question here is, how can we use data to improve upon such a process and to make it adaptive to evolving information? In effect, how to combine this forecast, and taking this one step further, how can we combine forecasts in such a way that accounts for the downstream decision-making process? So I don't have here anything methodological. So using the same methodology that Wangkun provided earlier, we can implement what we call here application-driven or decision-focused linear combination. So we assumed the case that we get a collection of forecasts. In this case, there are probabilistic forecasts in the form of a probability density function, and we linearly combine them into a single distribution. And we implement a method that optimizes these weights in a way that finds the distribution that leads to the better downstream decisions. And these weights are also adaptive to evolving information, such as the weather or the day of the week, etc. And some very brief results, we consider a problem of a solar aggregate or participating in a day-ahead electricity market. So they offer their production, and then they are let's say they are penalized based on deviations. This is a trading application. And what we saw here, ineffectively, is that having a model that accounts both for the downstream decision cost and the accuracy of our forecast led to better trade-offs in both cases. So let's examine, for instance, here the circle markers. CRPSL, effectively, it's the method that only accounts for probabilistic forecast accuracy by minimizing this scoring rule called CRPS. So this is the equivalent of RMSE for point forecast. And DFL are methods that account for the decision of the downstream problem. And as you can see, there is a tuning parameter that trades off between these two objectives. And basically what we see is that by accounting for the downstream decision task, which is the trading cost, we manage to reduce the trading cost. And the most interesting thing is that actually, if we are combining these two objectives, we bring out the best of both worlds, and we manage to get both excellent statistically accurate performance, but also reducing the decision-making cost. And I think this concludes my this part on forecasting combination.
Okay. Okay, thank you very much. Let me ask one question based on an observation from other work I've seen, and then we'll move into the Slido questions. I've seen comparisons of results of production costing programs, just the conventional deterministic ones, deterministic forecasts with probabilistic production forecasting. And if people get, a 1% improvement, 1% cost savings using the probabilistic production cost savings, savings from the production cost program, they get pretty excited when they see 1%. And I saw, 4% in the example that you presented in the earlier part of the webinar, and numbers between 1.5 and 3% here. They look like very large numbers compared to numbers I've seen before. I'm just curious, what kind of other comparisons do you have, or have they been tried out in any benchmark cases with real systems, or is it all a result of the sort of analysis work that you've done here?
Yeah, thanks for the question. I think it's really important to kind of clarify this point, because we are actually testing our algorithms on a simulated environment. Therefore, we can definitely find some data set about describing, for example, unit commitment or redispatch problem. However, there are some systematic parameters, for example, some cost of a flexible generator that we cannot find. Therefore, I just searched in the literature to give a relatively reasonable values to this missing data. And yeah, therefore, I think this 4% reduction might be a little bit over optimized, because eventually this study assumes that we know the perfect knowledge about what's going on in the grid, and what it will going on is actually used during the training. So therefore, I think our results represent a over optimized, maybe a upper bound of this kind of solutions. And in reality, it's during so many unknowns about the grid. Therefore, I think the reduction can be lower. I hope this can answer your question. Thanks.
Yes. It would be very interesting if you could find a host utility to work with to.
Yes. Yeah, we are eager to test our algorithms based on more realistic scenario that is actually happening in the grid.
Yeah. If we have any takers that are participating, we'd be glad to hear from you if you're interested.
Yes,
Okay,
of course. Yeah.
Move to the Slido questions. The first one there about presentation being made available. The answer is yes, it will be available in the next couple of days. Then an email will go out with that information. So, do you see more granular time steps, 8760 versus sub-hourly, being more useful? I'm sorry, do you see more granular time steps, I guess sub-hourly? Which one do you see as being more useful?
Sorry, this question is for my part or for the missing data?
I guess it would be, I think it would be for your part, Wangkun.
Yeah, to be honest, I didn't try a more higher resolution data because it's more about a real-time balancing, or if it's the resolution is even higher, then it will become a control perspective. And at that time scales, I don't think the operation cost will be the main focus of this kind of activities. By theory, I think there are still some improvements by using, if you can better define downstream activities associated with a higher resolution time series steps, then I think it definitely has some improvement. But yes, depends on what kind of operations you are really focused on.
Okay, thank you.
Thanks.
I guess looking for an opinion on what would be the best public available data set to explore these ideas. Are you aware of any sort of public domain data sets that you could play with these ideas?
Yes. I showed them the GitHub. Yeah, in these slides. This is my GitHub. I have some open source data. Yeah, the data is from an open data set, which has a detailed descriptions is included, I think, in the previous slide. And I have some
in the
algorithms
footnotes, I
to.
guess.
Yes. Yeah.
Yeah. Okay.
Yeah. You can
We can
play
look at the
about it.
footnotes
Yes. Right.
when the slides up. Okay.
Yeah.
Question, what's your view on feasibility of such an approach in real size power systems and market optimization problems?
Yes, I think, as I said before, I think the idea is really promising. But what we done from a research perspective is maybe we overcomplex the problem by using a very detailed unit commitment and redispatch. However, as you can see just in these slides, the right images, by running this kind of algorithms, it actually gives you lots of insight by just to see this the detailed distributions of the forecast error versus the operation cost. I think a system operator may not actually use the exact algorithms that I propose, but they can take over some insight about this over forecast and under forecast. And most simply to try, most simple thing to try that you just associate a larger weight to a, for example, an under forecast load, then it can give you some benefit when you actually deploy the forecaster.
And if I may complement Wangkun's answer, the response is great. Of course, this approach is more challenging to train a model. So there is higher cost to train a model, but this cost is an offline cost, which is great. It's not operational cost, but there is no extra cost operationally at inference. So basically, you can still just get a deterministic forecast and then solve the same problem as you used to solve before, but get better decisions.
I also want to, sorry.
Oh, go ahead.
Yeah, I just want to highlight in the summary page is that because we only change how the forecaster is being trained, therefore it will not influence any activities after the forecast, which, to our opinion, maximize the feasibilities or applicability of this kind of innovative idea.
Okay, and just curious, with the training, depend on the system that you're training on? I mean, if you train on one system and you run it on a different system with a different generation mix, would you expect it to work equally well?
No, I don't think so.
Oh.
Yeah, because what we really care is the performance of a specific optimization problem. Therefore, we intensively to fit our forecast model based on this kind of observation or the optimizations in hand. Therefore, if you just like all the deep learning method, if you want to directly use the same model to a totally different circumstance, it won't work very well. Yeah.
Okay.
Thanks.
Question here. Is there any real world application of this application-driven forecast? I guess, is anybody using it? Have you tried it on any real systems? Similar to the other
I do
question.
know that some system operators are aware about, for example, some reserves are very costly. They will actually change or manipulate the forecast value a little bit to focus more on the, for example, a heavy load in the future or the very costly reserve preparations. Yes, it is reported in some report and literatures. Yeah, if this is what I think is all followed the application-driven forecast idea.
Okay. A question related to the earlier question. Let's see. If the model is trained on 8760, how do we get to forecast shorter time intervals? Not sure.
Sorry, I'm not sure about the question. So it's about to get a higher resolution forecast, or
I think that what it's getting at.
yeah.
Right. So how do you get to the higher resolution forecast? Shorter time
I
intervals.
think right. I think that might not very related to the application-driven forecast, but there are some certain techniques, for example, to improve the resolution of the time series data. For example, imputation is definitely a solution, and also you can train a specific, a more dedicated neural network or machine learning models to fit in this kind of task.
Okay. Question on what is the coverage for optimization in your study? Optimizing a single point may be a lot easier than optimizing across a portfolio or geography.
Yes, because in this case study, what we focus on is a transmission level activities. Therefore, we have to consider all the interactions between different buses or different nodes, and to imagine ourselves to be a system operator of the whole systems to maximize the benefit of the entire system. Yes, of course, if you only focus on a single location or single bus, and if you can better define activities of this single bus, then yes, it becomes much easier to train this kind of model. Yeah.
Okay. Could you describe generally your vision for the forecasting, optimization, control, integration? How would you see that working in practice?
Well, I think because we know that there are more renewables and more inverter-based IBRs into the system. In our opinion, we think the previously, for example, the model-based method may cannot be that flexible to cope with all this uncertain component. Therefore, we would like to break the boundaries, for example, between different time horizons, from forecast to operation to control, and to take a more systematic point of view to try to optimize all these stuff together. For example, at the forecasting stage, we now consider how the operations will in turn impact on the forecast, and what the forecast can better fit to the operation. And of course, in the operation, we can also find a more, maybe you can see a more conservative static operation point, then can make the follow-up control easier. To make the basically the idea is to make the system more flexible by introducing more decision variables into the decision making.
Okay. I think we probably got time for one more question here. Got all three left, but let me see if we can fit this in. How does your optimization formulation capture all the nuances and uncertainty in the energy markets? And how is it fed to your AI models?
Akylas, would you like to? It's more related to the energy market, I think.
Oh, I I think
You want to
the
repeat
question is
it,
for the
Akylas?
second part. Could you repeat maybe, Charlie, the question?
Yes. Yes. How does your optimization formulation capture the nuances and uncertainty in the energy markets? How is it fed to your AI models?
Well,
Does it-
I guess this accounts for the application-driven forecasting, but
Yeah.
unless it was for the forecast combination. But in any case, we have a stylized model of the market. Whether it's the trading problem, we assume that we are a risk-averse producer that has some sort of like target goal about the trading cost. If we are the operator, we want to minimize the total production cost, of course, subject to the grid-related physical constraints. In an abstract form, both of these can be formulated as an optimization problem where we have somehow a cost function that we're minimizing and a set of constraints. Ideally, we want this to be convex. It might be non-convex as here in the unit commitment problem. The way this is integrated in the machine learning model is that effectively we train neural networks. Usually we do what is called backpropagation. So we do a forward pass when we estimate the output, find an error metric, and then we take a gradient to update the model parameters. What we are doing is we are embedding this problem within this pipeline. So at each forward pass, we generate a forecast, we solve the optimization problem, and then we find how much the cost of the optimization problem would change as a function of the model weights, and then we propagate through the problem, and this is what updates the model. And in the case here, when we integrate a problem that is, let's say, non-convex as the unit commitment problem, we can employ different tricks, such as taking a relaxation of this problem just to help the model learn easier.
Sounds like it's baked into the process. Okay, we're a little past the top of the hour, so we need to wrap it up. I want to thank Akylas and Wangkun for this very informative webinar on the applications of AI to operational forecasting, a little bit of a new thing here. I think it'll serve as a great source of new ideas for those of you working in the field. And as I mentioned earlier, an email will go out once the video file has been posted, and we'll answer the questions we didn't get to. There's only a couple of them left, I think, and get them posted as quickly as possible. We appreciate your participation. And if you'd like to stay engaged, I'd like to invite you to participate in the next ESIG webinar on March 12th on visions of future electricity markets, featuring an outstanding slate of market design experts. I'd also like to invite you to have a look at the ESIG Spring Technical Workshop in Austin, Texas, during the week of March 17th. There's still a couple of weeks to register and another outstanding lineup of topics and speakers. Further information on all of our webinars and events can be found on our website at esig.energy under events, and you're all invited to attend. Information on all the G-PST webinars can also be found at globalpst.org. Akylas and Wangkun, I want to thank you again for this very timely webinar, and thank all of you for your interest. We look forward to seeing you again in the near future. And in the
Thank you for
meantime,
the
everyone,
invite.
take care, stay
Thank
safe.
you, everyone.
Thanks again for your
Thanks, Charlie.
participation. Okay, see you soon. Bye-bye.
Bye-bye.